Start recording. Okay. So last time we did, we talked about.
Nothing.
Sorry.
Nothing. We didn't do any coding, but yeah, it was good.
No. Oh yeah. We did. Yeah. So we did review. So that we did the pigeonhole theory with our 3 happy little pigeons, and then we talked
Twitter,
about
Canon, and Qbert.
Yep. We talked about and, or, and exclusive or, and how they worked. So you mask out things, so you just get the lower bits here. You combine 2 different things you already masked here into one thing, or you exclusive or, and it's like a selective inverse down there. So it's sort of
Right.
overlap combine. It's like combining the information in there, so which is a useful thing if you've got a hash. It's like it's not a particularly arbitrary thing, so it's not a the values are arbitrary that you get, but the process is sort of based on information. And then we talked about shifting as well, so it's like you shift left and you shift right. So one thing that I'm going to quickly introduce here on a new whiteboard is let's get some. Right. So if we've got some bits, we can also do a shift on them. But instead of a simple shift, this is going to be a rotate, and so it's exactly the same as a shift. And so if we rotate left, these bits go here, and then this one jumps off the end and comes around there. So you remember our last thing about the way these things tend to be wired up. Certainly we don't have a carry bit in this situation, but like in a normal system, if you've got a shift, you can like select between it's like which of those are we going to select when we do the shift, and so we select this one if we're doing a rotate, and we select this one if we're doing a shift. So the way this is implemented in hardware is fairly sort of straightforward to add a rotate when you're designing the silicon for it. Make sense?
Yeah. Is there? There's no operator for this difference, right? Do we have to implement it ourselves, or is there an operator for rotation?
So this is where we're going to get a bit sad. So we're going to use this very shortly, and unfortunately, we're going to be implementing Murmur hash, Murmur hash 3 specifically. Here's someone's that they've prepared earlier. Here's their rotate left, rotate right, and you can see they've had to implement it by doing a shift and then shifting the last bit back to the end, and then doing an OR to mask them together, because they've shifted in zeros in both of these cases. So it's the OR is going to ignore those zeros, and it's like it's pre-masked effectively,
right.
And then combine them into a single value. Whereas, and I hadn't looked at this, but I'm going to make an assumption this is the case. If we come over here, you can see it's using this ROTL32, which is a macro. Hopefully it's in this file. Oh, okay, so here's where it gets slightly annoying, in fact. They use a function for it. Oh, actually, no, sorry. So these functions are, I'm guessing, defined in standard lib, and what you'll find is these are going to be CPU intrinsics of some sort, and they will compile down to a single instruction.
Right, and those other ones are the graceful fallbacks for when you don't have that.
So, not only are they the graceful fallbacks, so this is Visual Studio, so Microsoft's compiler has these, and we can probably look up the documentation for these. Whereas anything that's not Microsoft, so we're talking Clang, we're talking Clang and LLVM, or GCC, they're going to compile this. But what you'll find is that Clang and LLVM, and I know this because I've actually checked, because I've done this, they will look at this and be like, oh, that's a rotate left. Or that one, oh, that's a rotate left 64-bit. And they will just swap out all of this and drop in the appropriate CPU instruction. So they're actually
at compile time, right?
Yeah. So when they generate, when they do their optimization phase, they will go through and replace this with a rotate CPU instruction, and they're clever enough to do that. Here's the documentation for Microsoft's things. Doesn't really say anything useful about them. Don't know if anyone.
So does C# have this idea, or do we have to just like use manage code?
So as far as I know, C# does not have one of these, and the JIT will not do this optimization. I could be wrong about that. We could check, but I'm pretty sure they won't. In fact, why don't we check? We have the thingy. Let's see if I can. Do we remember what the thingy was called? Because I've just forgotten. I know the other one was Godbolt.
SharpLab.
That's the one. SharpLab.io. Thank you. So, seeing as we have this, we can just grab out not that one. Well, actually, we'll just grab this one, and we'll convert it. Static. Let's fix all this. That's an int. That's rotate left. That's an int. That's an int. In fact, there's going to be uints because that's probably going to make our life easier. What errors have we got? Uint static. That. Oh, sorry. Static. Sorry. Int that. Okay. And already we can see, this is the JIT. That does not look like what we want. Let's actually bring up
one instruction
and have a quick gander at what LLVM does with this. I hope that's the demo and nothing important. Oh, actually, I think that's something from Casey. I think that was bits of Murmur, meow hash. Where to go? Oh, it's over here. So compilation failed because it doesn't know about that. Oh. Remembering how to code in this. Okay, so here we go, and then there's our one instruction, and this is on Clang. Even this is on MSVC. We'll do the thing as ROL. So shift rotates the bits, the first operator, the number of bits, blah 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 blah. So this is our one instruction way of doing this.
Oh, that's too bad.
Yes. So we're losing quite a bit, actually. There's a shift, there's a negation, yeah. So we've got a whole bunch of excess instructions here. It's not like they're slow instructions. This will still be quite fast, but it could be 1, 2, 3, 4, 5, 6, 7, 8 times faster, give or take. Which is not all that surprising. Are we in release mode and everything? Yeah, let's...
Seems like a nice bonus to try to see if that works better with interop. Well, not today.
Well,
oh yeah,
because it's one instruction. I'm just like, can we upgrade the version? Is there a new one that will do fancy stuff? And it's like, oh, it's still loading. I'll leave that off in the background. But yeah, so the thing about interop is obviously interop is substantially more than one instruction to switch out of managed into native. So you can't. It's never worth it for reducing 8 instructions to 1, sadly. However, if we would
Fair,
implement...
but maybe it was only 4, you'd still get twice the speed or something. But
yeah, like it's something you'd measure.
yeah.
I don't know what the cutoff is. I just assume that it's the one instruction. Like, no. But what I would do is like, all right, if I need that speed, I would take the whole hashing function and implement it in C.
Right, that makes a lot more sense.
Yeah. So let's get cracking with this.
Yep.
So over here is the... we don't need the Wikipedia page because it's not very useful. That's not it. Here we go. So this is the... I don't know why. This is what Wikipedia links to for Murmur Hash 3. Introduction, Murmur, successor to Murmur Hash 2 comes in 3 variants, 32-bit version that targets low latency for hash table use. So that's not what we have. 2 128-bit versions for getting unique identifiers for large blocks of data. That is what we have. So we want unique identifiers.
Yep.
And hopefully the fan noise is not coming into the microphone too much. I can see it on my little meter. It's like tick, 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 but yeah.
Oh, it's barely noticeable.
Oh, good. Okay. All right. So this is the pattern of Murmur hash. So K is a block of the key, which I think is 32 bits. H it could be 64 bits. Yes, sorry. K is a block of the key that's 64 bits. H is a block of the hash state, so this is where we're sort of accumulating the hash into. And then N, Mn, and Cn are constants. So this is the mix function, I guess.
Oh, I see. Just like we were picking semi-arbitrary values for the avalanching, that's what the constants are doing here.
Exactly. So for each block of the key, we premix it using 2 constants and a rotate. That looks like that. So they're premixing the key. Mm-hmm. Then you just jam it into the hash block, and then mix the hash block.
Cool.
And then they do the finalizer. This does the avalanching step to make sure the bits that are getting changed are avalanched across the output hash. So I believe the theory is so that you change 1 bit in the input, you change 50% of the bits in the output, roughly. And these are the codes for 32 bits and 64 bits, and so you can see they've got different constants, but the structure is the same. And then it tells you how they come up with these constants. The constants for the finalizer are generated by a simple simulated annealing algorithm, with both of the avalanche all bits of H to within 0.25 bias.
So that was the idea that you mentioned last time about sometimes they use like machine learning kind of to like figure out the
exactly
constants handpicked by people.
Yeah, it's and in fact it is basically a search. I mean, are you familiar with simulated annealing?
I heard the term before, but I couldn't reiterate it now.
I mean, it's not something we need to go through, but for certainly if anyone watching, it's like here's the Wikipedia page, and basically you start with
fitness function.
I'm not reading that, but you start with basically you start with a whole lot of guesses, and those guesses can jump around a lot on early iterations, and as you move later into the search, the amount that the guesses can jump around is reduced.
Oh, interesting. So it's not like genetic algorithm where you're basically just almost random and then using a fitness function and then only changing a small amount of the resulting, like I guess you call it like mutation. It's more like you make it harder every time.
Yeah. So the idea is like if the terrain that you're searching is like that, that's not very good. If it's like like this, if you're doing say just a crap search and you start here, well, actually no, if you start somewhere not very good like here, it's like, oh, I can get better this direction, so I'm going to go this direction. And it's like you're there and you go to this direction and you're there, and it's like, oh, and now I'm stuck and I'm done. whereas in simulated annealing, if you're here, it's like I feel it's better to go this way. I'm going to make a big jump, and then I'm just like, oh, better this way. I'm going to make a big jump. I don't know. I'm just like roughing it, but I'm going to make a big jump down to here, and then as you move on, the jumps get smaller and smaller. I think the terrain here has not worked for me, but basically the idea is you end up in a situation where you can jump out of these little local maximum.
That's the local maximum. Yeah, that's what I was thinking it was. Yeah, that rings a bell.
And so you can imagine so I think the idea behind this is like a noise function, some sort of forms of noise have like low frequency oscillation, I guess you call it, and also like high frequency oscillation, and they all combine together, in fact, and then higher frequency still. And so the idea is you find a good spot in like the low frequency areas, like this whole area is crap, and so when you're doing big jumps you end up heading this direction, and then when you're doing smaller jumps you actually, it's like, all right, now we're going to head like into from say here to here, and then once you get here it's like, oh, this is not so good, this is better, and we end up like here, that sort of thing.
How are the jumps determined? Like you said it was a search, but the jumps kind of look random.
From memory, there's a random element and a directed element, which is why I had trouble here, because I'm like, oh, hang on. So it's like, and the thing is, you don't simulate just one point, you simulate lots of points, like you do the simulation multiple times, effectively.
Right.
Something like that.
So it's like there's a gas pedal that's random, but the steering wheel is predictable. Is that what you mean?
Kind of, yeah. So I mean, this is my vague recollection from.
That's okay. Next year we'll do a whole thing on AI, so it'll be fun.
Yeah, absolutely. So basically the point is, the jumps. Simulated annealing is like the jumps get smaller. That's sort of all you have to remember until you actually have to go and do it, and then you like look at the Wikipedia page and the implementations that people have done. So you can imagine that's how they found these constants. It's like, we found some sort of vague areas where these constants are good, and we're going to narrow in on like better ones within them. Once we're going to sort of like find the higher bits, go down to the lower bits. Although these may, actually, I don't know if they actually. I suspect they might work like that. Like the upper bits are more important than the lower bits, but that's probably the first thing you'd think about when you're doing this. Is like, what are the big jumps? What does a big jump mean? Like, what do these bits mean? So
yeah.
Anyway, that's roughly. It could also,
for our purposes, we know that they're fixed. They're not like not like hash code guessing.
So yeah, so they've done the work for us and found what these values are.
Cool.
So the 128-bit variance mix multiple blocks of the key data in parallel to ensure that all the intermediate hash blocks affect each other. Use separation, simple operations interleaved with the block mix. So it sounds like you mix the key, you mix the hash, and then you do some mixing of the blocks. So it sounds like it's the hash is 32-bit blocks, and you need to mix through them or something. But that's fine. Like, I don't think we'll try and implement it off this. I think we're just going to go straight with the C++ source. If I can find it again. Did I close it? Maybe I closed it.
I could use the RCRU source, or is that cheating?
Oh, I mean, yeah.
That's
like,
copy paste. No, we should probably look at ours after we actually do it. And
well, I was hoping to implement it off the the pseudocode here, but
Okay.
I actually need to figure out what the interblock mix where that is. I mean, the C# source I have here looks like it's kind of crap. Like not exactly what we want. It's simple, but not
Right.
the way we want to do it, because it's like split up into a whole lot of functions. And it's like, well, if you're sticking function calls in there, that's not what we want. We want to minimize that.
That's is that to minimize jumps or
Yes.
Calvert or whatever it is? I don't remember if Calvert is basically the same thing as a jump or not.
Calvert is the one that inserts a null test, basically.
Okay. For overrides, right? That's because it's virtual, so it needs to check to see if there's an override before calling the base.
That sounds familiar.
It table doesn't matter. I don't want to sidetrack it.
We'll stay vaguely on topic at the moment. So, okay, so here's the implementation now. We want the 64-bit because
I thought we wanted the 128. Oh, 64-bit
implementation of the 128-bit hash. So I think we figured that we're going to be 64-bit. So this is why we can't copy, in fact, the River City one, because the River City one is 32 bits.
Right, that makes sense because we knew that our game fit nicely into 32 bits, but we're building a library, so we want extra space.
So let us begin. Let's look at what we've got. We've got the next ID hash, and what we've done here is we've just said there's two different hashes. We get an ID for like a string in either case, and we munge it together with an ID hash, which can be an integer or a string. So I think we'll worry about that later. For now, it's just enough to implement a get hash code, and I think let's just do it with string. So let's just say this. Copy this function signature down and say remember hash 3. And let's start implementing things. So you might want to just zoom in one level so certainly so I can see what's happening. And so let's start looking through this code. We've got some stuff, we've got some seeds, we've got some constants, we've got a body. Okay, and so this is our block function, and this is our tail function. Okay, so the tail function, this is how they deal with the case that you have got a whole lot of, like, your data length is not 16 bytes, sorry, 8 bytes.
So this is padding for alignment?
So yeah, this is padding for alignment, and
okay.
I'm sure there's a reason they've done it this way, but I'm curious. Oh, okay, so they're tails that. I'm just trying to read what they've done here. Okay. We'll worry about that when we get to it, and then the finalizer is actually quite simple. So let's start implementing this function. So, in fact, let's start based on... so I'm just thinking about how we will do this best, because it's 64-byte blocks. 64-bit blocks. So I wanted to make this a bit more interesting. So yeah, we'll do the 64-bit way. So I guess I think the easiest thing to do here because just to save a whole lot of typing is just to grab this and copy paste it. This is pretty sure at the top of this says it is disclaimed copyright, so it's basically public domain. So we can quite happily just grab this and copy paste. So I'm just going to drop you the link to this in Slack. And it will still give us a lot of interesting things to go through.
Sorry, just give me 1 second.
No worries.
Have stuff on there.
We'll cover up your screen in case you need to do anything. Your screen is now covered on my end if you have to open stuff.
Oh, yeah. Okay. Yeah.
Just give us a shout when your screen is clear.
Yeah, you might just want to, whoops, you might want to just snap this little section off if you...
No, I've got a dirty great chunk of source code covering your monitor.
Oh, okay, sorry.
So you can open up whatever
I
you
do
like.
business stuff, folks, sorry. Yeah, okay. What's the name of them? I've got it up now.
Oh, you got it? So it's the
name?
last function in the thing. So it starts at line 255. Okay, so screen is coming back, and now I'm back. Okay.
Okay. Permission for... Okay, so, yeah.
So...
That one... I got some scoping issue there, but that's fine. Oh, I see. I just screwed this up. Yeah.
Yeah, so this is good because this will save us a whole lot of typing. Like, it's no point.
Yeah, for sure. Just basically make good.
So, I mean, we are implementing someone else's code, so there's no real shame in just like grabbing it. So,
yep.
Let's start talking about let's start doing a straight conversion of the data types first. So we know that uint8 is byte. We know that we don't have
uint8. The underscore t. That's that magic function.
So
that's byte.
Underscore t is I think we discussed this. So like basically,
yeah, we did.
The types in C and C++ are nuts. So people started introducing their own version of that, and then they finally added this thing to the standard. But because everyone already had it in their source code, they had to stick an underscore t on the end of it.
Right.
So
it's essentially a macro, right? Or is it? It's actually
it's
a type. It's had to disambiguate. It's sort of like a not namespace postfix as opposed to like NS URL or something.
Well, I can tell you exactly what it is. It's something called a type def. So
okay,
this is not a thing in C#. The closest thing in C# is like using foo equals system dot diagnostics dot debug dot So I can rename types up here using the using statement. It's basically that, only you can do it like with integers, for example.
Okay. You can teach me all about that in our C++ stream.
Absolutely.
So that's iterate, basically.
So this is long. I'm going to keep it with uint64 just to make things clear.
Oh. Okay. So you long? Oh, you're not. Yeah. Okay, you're using the full name.
Yeah. So I mean, I'm just like, what is it? It's ulong. I was like, well, I've forgotten how long ulong is. So let's just actually write 64 there, so we know that we've 64 bits.
Okay.
But I mean, yeah, we can do either. We don't want const because that's a C thing, really. Okay, and so now our squiggly lines are down to like the stuff we actually need to focus on.
Gotta get rid of a couple more consts. It's weird that they oh, it's not weird, but I don't know why they do the const thing if it's not.
I mean, if we
writable
wanted it, it would be the equivalent of doing read only.
Oh, but we can't do that. That's
not valid for this item, so that's fine.
I thought we could only do that in private declares for like class states, but that could be.
Yeah, there's a.
It kind of reminds me of final in Java, but it's been too long, so I can't remember now. All right, so get rid of this pointers. Those are arrays.
Well, I mean, yes, we could do that, but maybe don't do that just yet because.
Oh, we might be going unsafe. Yeah, I didn't think of that.
Well, we may be going unsafe for starters. But the thing about the pointer is you can see, so now I can start talking about what's going on here. So you see where data is coming from. Where is it?
Yeah.
Actually, where did you get that?
Coming from
blocks. Blocks. Okay, yeah. So we're actually taking the data and we're dividing it up into 64-bit chunks to do processing per block. However, our incoming data is just an arbitrary pointer. Like you can remember that key, which we've erased what this was, but this was a void star, I believe. So it's like we can take any pointer. But yeah, so keep it as pointers for now because that's actually meaningful.
Yeah. So
now we've got our string, and what we need to do is we need to treat this string. So let's go through and fix up everything that's not touching key or data. Seed we might look at as well. Okay, so C# I think automatically does this. Yeah, so just stick a U at the end just to make it unsigned.
Explicit.
Seed, we'll pass in seed just for the sake of completeness. It's probably going to be 0. Set equals 0. Blocks, okay, so we're looking at something from data. Get block 64, so we've got to implement that. We've got to implement rotate left 64. We're looking at some data from tail again. We've got K1 and K2, so apparently we've already got, okay, so we've got a scoping issue here. So this is fine. K1, K2, yeah, they stopped being used, so we can just take that and we take this whole thing and give it a scope, so it's not in the same scope as the other K1 and K2. Length we know is the length, so we'll worry about that in a sec. We've got fmix 64, and then we have the output, so we've got to come up with an output type as well. So let's start with like the little bits. So we've got rotate left 64. This is actually quite easy. We can go back to the source code and just pick up rotate left 64.
Yeah, I'll just grab it.
Give it, yeah, I'm gonna give it an all caps name just because it's the same as what they're using there.
Like this. Oh, it's just oh, I totally. I got a scope line in the wrong place somewhere. That's fine.
Okay, so
still don't have length or len.
Oh, I didn't notice that you'd copy that in there. So I'm taking it you've got rotate left 64 correct. And
yeah,
before we move on from that, I like you understand perfectly how this works.
Let me see. So this
possibly,
yeah. So
let's draw out the diagram just to. So this is what we're going for in the red lines.
Well, you're rotating R amount. Yeah, you're doing R shifting.
So what we've actually done is we've done shift 1, 2, 3, 4, 5. So we've shifted left here, and then we've taken the top bit and we've done a shift right to there, and so we've actually got. Sorry, I'll do it slightly different. We've got that, and then we've got now. We've got a 0 here, and we've shifted everything off here, so we've got 0, 0, 0, 0, 0, 0, and then we just OR them together to get the final value, which is the mix of the two.
Right, that's how you get the equivalent of moving the value, because if it was a 1, it would have showed up as a 1 when you ORed it.
So you can see how that's the green is equivalent to the red, but it's like more steps.
Right.
And that's exactly what we're doing here. So
yeah, I just didn't quite understand the 64 minus R, but that's basically just taking the entire bit, and then that's how you get that's how you calculate the number of spaces to shift right to get to the end, right?
So,
it's taking
there's
just a difference.
The incline of this line is basically the case, because obviously this is a shift by 1, but this is an arbitrary shift or an arbitrary rotate. Okay, get block 64. What is get block 64? Okay, so that's just an array access. So I'll just make a note of that for later. We won't worry about actually doing that yet, because I think we'll just implement that straight up. Length, we've got the tail, okay, and then we've got this f mix 64. And so this is a finalization mix, so it can also, this is also a chunk of the thing. I think I'll just grab it and stick it in. That way we get their constants. And you'll notice I've made these all private static as well.
Oh yeah, I haven't bothered with that part yet. Good.
Now one thing we could do here, however, what am I running in? If I hit properties on this, I am .NET 4. I believe you'll be higher, so you could do method in
aggressive inline?
Aggressive inline, if you were so inclined.
Find it. Forward, no inlining, synchronized.
You may be .NET 4 as well, which doesn't have this available.
Well, I'm using FNA template, so probably whatever that is, which is probably.
But that's fine. We'll mark it as to do, and we'll worry about that later.
Oh, that's fine. Okay. Yeah, and plus, I think I would love to hear a thorough explanation of that. I've used it before, but I most likely don't have enough understanding of it, so that'll be helpful for another time. All right.
Okay, so now the last thing we have to do before we look at actually what data we're using is we need an output type, which is basically two 64-bit values. So you can see that we've just got one 28-bit output value. So exactly what you're doing there.
I just remember that type from the game.
Yep, that's pretty straightforward.
But I know there's a lot of sort of helper and operator overloading stuff that maybe we should just steal from Serializer.
Quite possibly.
Or we
Let's see if I can find it real quick.
Hub pixel 3D serialization.
Oh yeah, so
Oh yeah, I moved it. Pixel 3D.
Tree. Can I just get the master?
Source.
Here we go. So I'll just copy this one to get stuck for you. Although, but it's source pixel 3D common value 128.
Oh, in common.
Yeah.
Used to be in. Okay, I can't remember why. Whatever. Oh yeah. Okay.
So it's actually like a lot of this. I suspect is just get.
Oh, that's interesting.
It's actually quite simple.
I was gonna do it with 2 longs, and you did it with 2 ints. Is it
well,
relevant? Maybe
you'll recall.
Probably is. Yeah.
You'll recall that our implementation in River City was 32-bit. The 32-bit version of this, and we're doing 64-bit, so that's fine.
Right.
So what we do want, I don't know why get bytes is there. I think it might just be for debug output somewhere. But we do want operator equals because like literally the only thing we do with this is compare it. So let's call it, let's change these to V1 and V2 so that we're not going insane by having A and B there. Don't need the bytes, and let's just grab in the object, the so-called object guff.
Oh, we don't need 2 bytes. I can code that.
Yeah, I don't think we need 2 bytes. So I'm just copying this in from this for people playing at home. Get hash codes, just nonsense. Let's put that in a region and collapse it, and it can go away.
Just saved, just saving the typing, right? Alright, so I don't need 2 bytes. Fair enough. Okay.
Yeah,
bye.
so the important thing that we did there for people watching is we implemented equality operator. It's like, this is really straightforward. So now we can be like, okay, this returns value, is it new? Now I've started coding in C, and now it's like, V1 equals H1, V2 equals H2, and that's correct. No. Oh, okay, there's a type conversion issue. So now we've got the correct return type. And yeah, I actually like what you're doing there.
Sure.
So, and then this does the trick that we talked about, where if you remove the new thing, it will warn you. I mean, it's completely useless for this case because no one's ever going to add fields to this, but like it will warn you if you add fields and it's not filled.
That's right.
If you wanted to be particularly aggressive about this, you could help the compiler out and just store H1 and H2 in retval and stick retval at the top, but let's just leave it as is for now.
Sure.
So now all we need to do is start thinking about the data. Now, this is a slightly unfortunate thing about the way we've implemented it here, is we're going to actually have to copy paste this thing, because as you saw, we had to copy paste it 3 times up when we did Jenkins, because we had the integer, we had the string, we had the string builder. But we want that sweet performance, so I think we're kind of stuck doing that. I'm just trying to think.
Yeah, we could use a T and do type checking on it, generic class, right?
Well, okay. I was like, well, is there a way to do that?
No,
not particularly.
No, I was joking. Just my typical joke about doing overly complicated stuff for no reason.
Oh boy.
Okay, cool.
So
when it's a seed, that's a random seed? Was that like a noise seed?
It's just like, if you want to... Is it? Yeah, it's like if you want to just start the hash off somewhere other than 0, it's sort of like, because it doesn't affect the hash, like we could pass in for seed, we could actually pass in the the next ID hash, for example, rather than doing this XOR business. And I don't know, maybe that might give us better mixing. It might not. It might actually be bad. I'd be inclined to probably do the XOR thing. But I suspect it probably doesn't make a difference in the grand scheme of things. So let's go through and just do this for string, keeping in mind that we might have to come back and do it for
right. That'd be a good warm-up for next session anyway, because it'll just be mostly copying and pasting and editing.
There's one thing we've got left, actually.
Length.
And that is, well, we've got length as well. So before we start thinking about where we're getting the data from, and that is this tail section. So where is the river city? That's that. I don't suppose you remember where the actual thing that uses that is. I guess I can just search for it. Hashing stream. It's like, does hashing stream actually do the tail case? It does. It does the tail case. I'm just like hash tail and finalize. Yeah. Sorry.
Just throwing breaks in here because it looks like the switches don't need breaks in C++.
No. So okay, so this is
sorry.
No. So this is a feature that they added in C#, which in general is a good thing, and that is in C. This is like a go-to statement. So it's like switch go to this, and then just keeps executing, and it falls through.
Oh, interesting.
And
okay,
this
so you can actually use it like a sieve, and multiple calls will get executed based on values coming out.
Yeah, so these all fall through, they don't break. And C# will not let you do that. You have to write go to case 14.
Okay.
Case. So in this case, it's actually more error prone, but because I'm having to hand copy it, go to case 12 and hope that I've got it right. Go to case 11. Case 10. Go to case. Oh, actually, this one doesn't need to go to. And so, hopefully that makes sense. So go to case 9, and this one does need a break.
No, I have no idea.
Actually,
why
it doesn't. No, it doesn't.
It
It doesn't need a break. See, this is why they got rid of it, because this thing's confusing as hell. This needs to go to case 8. Go to case 7.
Okay, so I do have to keep going. Okay. I was like, is that something about the hash function that I don't know, where the other ones don't fall through? Well, I didn't know you could jump out of a case and go to another one. That's neat.
Yeah, so like obviously they couldn't remove the feature entirely because, as we're seeing here, people do use it. So they had to add a mechanism for making that happen. Excuse me. And you can sort of see here, like, I know you've auto-formatted that, but you can see that the way this code is laid out here, it's much more dense, and you can sort of see the pattern in it a lot more easily.
Yeah, that was just ReSharper trying to be helpful for me. But
yeah, so ReSharper.
Editor config. Well, it's also editor config. I don't know if you're down with that, but a lot of people use like a .editor config file, and I have a default one, so I've never used this before, so it's defaulting to the pretty printy thing that's not helpful. So I'll have to change it so that it inlines these go-tos for me. Cool.
Still, so you know, this is all of that code. So let's start thinking about our data and where it's coming from. So what's happening is we've got keys, and they are strings that are made up of 16-bit blocks. and so we're having to expand that out to 64-bit blocks. So, and well, we want to keep the length the same. So what we're going to do is we're going to rewrite this section here. We're going to say int length equals key dot length times 2.
Is that 8-bit to 16-bit because of .NET?
So characters in a string are 16 bits.
Right,
So
but that's a .NET specific thing because they don't store it in UTF-8.
Yes, so they use UTF-16.
Such a pain in the butt.
Yeah, so that was like back when they decided to do that, it was actually not a terrible decision. I think this was Windows NT, like not even like, I think it was like NT 351 or whatever, or whatever that was.
I get depressed thinking about how many systems in .NET are written on 16-bit. Well, they all are, obviously, but like, and we always have to work with 8-bit strings. So like every JSON conversion thing, and everyone does that all the time, is always having to read it into 16 bits just so it can push it back out as 8. It's like performance destroying.
Well,
horribleness.
Anywho, there's a thought about improving that, but we'll save that. Key length. Okay, so this is our data. So data, I think, probably will just go away because we don't want to make this unsafe if we don't have to. Like, unless we're going to take the pointer to the string data, and I'm not sure you can even do that. Maybe you can with string. I'm pretty sure you can't do it with string builder, so let's not do it at all.
Okay.
Got the number of blocks. So blocks, we've got get blocks. So blocks and get block 64, like these things are tied in together. It's like we may as well just inline our own get block function. So we want to get, each block is 128 bits made up of K1 and K2. So that's all fine. So now we need to basically do the multiplication to get our blocks. So get 64, no, get 128 bits from key. So how do you feel about this piece of maths? I think we are slightly over time, so I'm actually going to say we might save this for next time.
Okay, but it sounds like we're going to do something very similar to what we did in the Jenkins hash when we had to kind of like shift things around.
Exactly. So in Jenkins hash we were going from 16. Jenkins hash was the easy case. We were going from 16 bits to 8 bits, and now we're going from 16 bits to 128 bits. So it gets a little more complicated because we've actually got to combine them out. But this is fine. So
the concept is the same, right? We're just basically pushing things down into the bottom of the 128-bit.
Yeah, actually,
or the two values, the K1, K2 values.
Maybe that isn't so tricky. Let's
excuse me.
Tail is okay. So tail, they're actually doing some nonsense there. So maybe we'll worry about tail next, and we'll finish up here. So
okay. I just assume that tail's going to end up being byte array because it's an obvious array access in the code. But
well, so we're actually going to have to do some finagling here. Not to mention the fact that we know that, like, for instance, we're not going to have case 15. Like, we're not going to have an odd number of bytes. So we actually have to put some thought into that.
Oh, that's weird. Are we doing padding and they're not in C++? Or like, is that a problem? With
no. So they're accepting, in the original version, they're accepting a arbitrary pointer with an arbitrary number of bytes in the length. But we know we've got this times 2 here. So we're never going to hit this case. So there may be interesting things we can do with the tail. So we'll worry about that next time. Let's finish up by just implementing K1 and K2. So I'm going to hand over to you to do this piece of code here. So we've got I, which is the block number we're on. So we have to do some fancy indexing, let's say.
Yeah. Right. So, excuse me. If I just say that hash is, well, I'm going to replace that with
so we don't need to worry about the thing that you've got there, the second two lines, certainly. Sorry, not the second segment, but the second two lines. So the part that's actually doing the hash, like, that's completely different in our case. But it may be interesting to think about the.
This is the yeah. Sorry, let me. The shifting is what we're trying to do. We don't want to and anything. Oh no, this is the part where we're masking.
So we're masking stuff out because we're splitting this 16-bit value into two 8-bit values.
Right.
Whereas what we're doing here is we're actually trying to combine 16-bit values into a 64-bit value. So we've got the 64-bit K1. But what I was saying is you certainly don't need lines 2 and 3 of the that's the jank. Completely different. But however, this operation is actually quite different to what we are doing because we don't need to split, we need to combine.
Yeah, right. Okay, hold on a sec. Let me just recover here.
That's okay.
Right. This is when you said split. That's okay. So and what I thought and was combine, but it's not. It's masking. So combine is or.
Mm-hmm.
So and then oh man, I can't remember the calculator with the decimal thingy to try to figure out where I'm moving it to. Hold on.
Well, I'll bring up the diagram from here.
Okay.
So this is.
That'll be the second time I'm doing it, so it's kind of like.
It's okay. This is why we're doing this one. Is to practice this business. So this is OR. So we've got like D, E, F, and the rest of it zeros, and we've got X, Y, Z. The rest of it 0, and we OR to combine it into a single thing. So what I will do.
Combining it against, well, I guess because 128 is always going to be bigger than what we're bringing into it, so we just have to OR it against the full length 128 bits of zeros, right?
Yes.
Would that do it?
Yes.
That would kind of fill it all in.
So let me draw out what we're doing here. So if we have, let's have a new. Today's diagrams are a bit rougher than last week's, I think. I was drawing hills. Okay. So let's see. We've got. This is our string, is string equals, and then we've got these blocks. And I'm going to say that each of these is 16. So, and then we've got, so each of these is an element in the array that is the string. And then we've got the value that is K1, which is part 1 of the key. And then this is a 64. So this is the correct width. So you can, if I draw in the little markers for, here's 8, 8, 8, 8, and then this is 8, 8, 8, 8. So these are bytes as the blue markers. But we don't need to really consider the bytes, but we do need to consider the 16 bits. And what we're doing is we're just copying straight down. Does that make sense?
Yeah, other than I thought that red arrows kind of. Oh, yeah. No, I guess oh shoot. Yeah, it does make sense. Sure. Unless we run out of 16-bit values.
So, and this is certainly something we need to consider. However,
Oh, I have to OR the 16-bit one with zeros of his full
well,
16-bit.
we know what happens when we run out of values to insert into our thing, because this is what the tail section is for. So we're
Right.
looping on blocks, and we've already calculated number of blocks to be 16 bytes, which in fact, yeah. So what we then have, we've got the same thing over here. So our character keeps going, you know, da 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 da, da. And over here we've got another 64-bit value, and this is K2. So I actually do this twice with more values there, if that makes sense.
Yeah, it does. I just, yeah, I'm having...
And then, so what we have, we've got, let's draw this a bit smaller, we've got this is our string. We've got 4 characters, because you can see there's our 8 bytes for K1, and this is going to be 8 bytes for K2. So this is our 64-bit value, like the zoomed out version. So this is K1, this is K2, and so this is a block. Yeah. So this whole thing is one block. And
right, but if K1 and K2 are both 64 bits, shouldn't we be doing a nested for loop then, because we're going one block? Oh no, one block has K1 and K2, right? Because one block is 128 bits.
Yes. So block. So this is equals 128.
Right.
Bits. So what we've done is we've basically divided up. So we're working on 64-bit values because that's what our processor width is. So this part is the code, and then so it's like, well, what's 128 bits of string? It's 1, 2, 3, 4, 5, 6, 7, 8 characters.
Right.
So what we have to do is just get those 8 characters into these two 64-bit values. So that's our goal here.
Yeah.
And so it's just a matter of doing the correct indexing and the correct bitwise operations to make that happen.
Right.
So,
well, if you don't want to watch me struggle with that, that might have to be a takeaway. Otherwise, I'm gonna, like, okay, so this is when we say I, that's a whole, like, we're getting from this string. That's only one character.
So, well, look at what
opposed
n
to
blocks.
one.
So we're iterating on n blocks. So this is block I equals 0.
Right.
So if we want to get specific, if we're in the string, we'd have to do some sort of multiplication by the blocks of blocks by this length plus, you know, if we want this one plus 0, 1, 2, 3.
Yeah.
So in fact, you can sort of see what's going on. They're doing something like this here because they're going I times 2, because we know that there's 2 64-bit values per thing, and there's plus 0 plus 1. So
you're right. So me getting the index actually involves pulling out the sections of characters from the key that we are looking at for this block.
Hopefully this pattern is like really familiar to you at this point. This I times 2 plus, or I times n plus k.
Yeah, that's the one we used to do when we were doing, basically using one for loop to iterate over something 2 at a time, like we did back in the day.
Exactly.
Our shape. Yeah, it's not familiar to me, but I know that that's what's being used. But yeah, okay. It's like key I 4. Key I 1. But that's not going to be a UN, is it? No, that's That's a weird compiler thing. These are actually characters.
So, um,
yeah, I know.
okay, let's excuse me. Let me try and draw out what we've got there. So, I'll draw this in orange. Actually, I'll draw it in
Bunch of
purple.
triangles all clustered together.
Blue doesn't seem like an angry enough color because this is not that I'm angry, but this is wrong.
Oh, for sure it's wrong.
I times 4, so already we've got a problem because we're going to be pulling.
I times 4 is 0.
Well, I times 4. I don't have a way of drawing this, but I times 4 is going to start getting the wrong data because on I1 we're going to be so I times 4 we're going to get, so on I equals 1 we're over here, and we're going to grab I times 4, so that's 1 times 4. We're going to grab this piece of data and stick it over in the next block.
Yeah, it's wrong.
Bad index. Obviously, the solution is this 4 should be an 8 because we're indexing by 128 bits, so you have to do that division. So it's 128 divided by 16, which hopefully is 8.
Interesting.
8, yeah. Does that make sense?
Well, because I thought we were doing I can see the K1 and K2 are both supposed to be 4 characters each. But yeah, I guess we're looking at it from key is being indexed on string, so it's characters, not bytes. So I thought for some reason that it was 4 bits at a time. So K1 would have 4 bits and K2 would have 4 bits, but it seems like not the same as the diagram. But
okay, so keep in mind that this is a block. So the block, I'll draw the block sort of in, I guess, yellowish. So
the block is a
this whole thing. Yeah.
Right, but when I guess what I'm doing here is I'm saying K1 is equal to 0, and then and this was saying is K2. Oh, you know what? That arrow where K2 is pointing? I thought that was pointing to the second section.
Yeah, so my bad. Let's fix that.
No, I should have followed you from the top part. K1 is the entire string of 8 characters, so obviously it's 8. Yeah, okay. Derp. Okay. So that's still wrong, right? But I know that.
Well, this is getting closer, so I'll try and draw out what we've got there. Now, so what have we got? Blue is going to be our color for this. So we've got key K1 equals I times 8. So we're getting 0 that one. So we're going to do that, and then we're going to go K2 equals I times 8 plus 1. So we're now doing that.
Wait a minute. Sorry, you just corrected it so that K2 is the second section of 4 bytes.
Yeah, so I've moved the arrow to make that make more sense.
Well, actually, okay.
So what we need to do is keep in mind that I've zoomed out. So this diagram here, that's a different diagram.
Oh, yes. Wow.
So just,
wheels are falling off. Okay.
That's okay.
So yeah, you said right. So obviously 0, but that's not helping. But then yeah, I times 8 plus 1 is putting K2 just into the second section. So it should actually be I times 8 plus 4, or yeah, no, 8. It's not 1, clearly. It's
So one was this.
Oh, FOIL, order of ops, right? You multiply.
So multiply happens first. So we're getting
right.
We're getting to there and then adding 1. So we're getting to here.
Right, but we don't want to be there. We want to be 4 over from there to the right.
Yep.
So I don't know why I wouldn't just say plus 4, but it sounds like.
Well, okay. So plus 4, we now have this.
Yeah, that seems right to me, though.
That's good. I mean, that's a good start. We've got 2 out of the 8 characters in the string into the correct locations.
Right, but we have to do a bunch of twiddly bits to get the rest of them down, right?
Yes.
Okay, so
So why don't we start with string,
boring the
well, the thing
rest
that
of
you had before, which was this element in the string. So this is key I plus 8, I times 8 plus 1 is going to be this guy.
yeah.
So let's try and get him
Right.
down into the K1.
Okay. Well, why don't we could just or equals him to K1 with key I times 8 plus 1. I'm not sure that would makes any sense though. That doesn't make sense. Hold on. I take that yeah, that doesn't.
Is this ours or is this theirs? Oops.
Oh, no, that's all me. This is them down here. This is me trying to do this up here.
Okay. Because yeah, I think that's just...
That was me Jenkinsing it up.
Yeah,
like
that's probably not wise to copy in a different algorithm.
Hi. I don't know what you mean. Explain. But yeah, I guess yeah, okay. So I feel like this is wrong, but I know that I want to take the character or the byte at that index and shove it into the long that is K1. But I don't think it's shifted enough to do that.
So what we've done here...
It has to be moved.
Yeah, so what we've done here is this. And you've just overwritten the thing. So
yeah, I got to shift it by 1 space to the right.
Mm-hmm. Now, so one space is... These are always measured in bits for shifting. So you would shift it 16.
16 because that's where it occupies in the...
So yeah,
0, 1,
now...
2, 4, 8, 16. Wait, no.
So this is 0 is here, this is 16, this is 32 and so on. So...
Oh yeah.
Not 64, 48.
Is it base 16 or something?
It's not base 16. It's just 16-bit blocks, I guess. Now, the other thing here is this is written in sort of, I don't know what you call this, like array order, bit order. But when the processor is thinking about, or when the language is thinking about bits of data, so if this is a 64-bit and this is a 16-bit, they're laid out in processor registers sort of from least significant bit to most significant bit. So sort of the same way you'd write a number like 412, like 412, you know, you'd write a number like this, like 0, 1, 0, 1, 1, 0, so on and so forth. So like a 16-bit value would be here. And so you actually don't want a right shift, you want a left shift. And does the reason for that make sense?
Barely.
So basically,
yeah.
So the idea is when you're crossing this line, you're flipping the way that you're looking at the data. So this is how the data is laid out in memory, effectively.
Right.
But this is how you sort of do operations on it.
Okay, that's totally new to me, but I get what you're saying. Because it's in bit order, it's positive, like basically like positive to the right, and then obviously in like binary order it's positive to the left, so I have to flip the sign if I want to move that direction.
So you can imagine a number like 7 would be 1, 0, 1 with a whole bunch of zeros over this way.
Yep.
And so, and you can store a 7 in a 16-bit number or a 64-bit number. It's the same here. It's like,
There's more zeros.
And so the idea is it just goes down. Like it's the same value, and you've just stuck a whole lot of zeros on the front of it. and it's ordered in the same way you do like maths, like in base 10.
Right.
However, obviously, when you think about it this way, you've got the problem is like typically you write left to right. So block 0 is this, block 1 is this, and so when you think about it this way, it's like 0, 16, 32, 60. Whereas in this direction, it's like 0. No, that's not quite a 0. 0, 16, 32, 48,
or
64.
Yep.
So you can see how that flip has occurred here. And hopefully why they do it that way?
Well, you can't access the data a different way than in bit order.
Yeah, but like why the way it's conceptualized in this way when you're working with like blocks of data, whereas it's conceptualized in this way when you're working on individual numbers or individual registers.
Right. Yeah, it makes sense because the data is being stored in the vector and it's contiguous in memory, so you can't really break it down.
Yeah.
Like because we're working on the individual components of a piece of data in memory. Like
exactly. So you have to be fluent in doing it this way and flipping between them.
Yeah.
As necessary.
Never happened.
And like in weird cases, like say you're doing like big int or something, you might, instead of doing it in bit order here, you might expand this out, you know, like 1, 0, 2, 4 or something, like hugely in this direction, and conceptualize a whole thing like this in weird cases like that. But most of the time you're doing blocks of data like this, and then it's like, oh, I need to munge one thing into the other. I'll flip to this thing just to do the operation.
Right. Okay.
So that's quite important. And so this kind of diagram as well is sort of something you kind of need to be happy making. Now, a bit shift doesn't accept anything other than an integer as the parameter, because remember, this is not like an addition where it's like we're adding a 64-bit number to a 64-bit number or combining it in some way. We're actually doing, we've got a number of some length and we're shifting it some amount, and the amount is only going to pay attention to, I believe it said like 64-bit would be the bottom 5 bits. 64 minus 1, bottom 6 bits, yeah. 5 bits is 32 bits. So what it actually does is it actually does a mask on the processor. So if I said bit shift by, let's get it down to a 32-bit value. If I said bit shift by 2111, the processor is just going to go and 63 and shift it 63 bits, or better yet, if I did 1035, the processor's not going to shift it all the way off the end. It's actually going to go and 63, and it's only going to shift it 11 places because it's going to ignore everything other than the bottommost bits. So K1 is that times that. That looks correct. That looks like you've done that. 16-bit shift that way. Yep, that's good. So now we have the pattern, so we just need to fill it out.
And K2.
Mm-hmm.
This is gonna be wait, okay, I gotta start. Oh, we already have +4, so it's just basically 5, 6. This is 8, 1, 2, 3, 4, 5, 6, 7. I still only want to do 16 because it's a new chunk. It's a new block of 64 bits. So am I good?
That is looking very good to me. I think that's correct. So the only thing I'd do now is just clean it up and get rid of the to-do and move K2 down to where K2 starts, so you're sort of all in order and stuff.
Right.
Just general cleaning.
Yeah,
Let me see.
get rid of the get blocks 64-bit. I like for var, so just that just because. kind of thing where I'm totally gonna forget this completely next time, but I'll need to find a way to get a review in. Okay, so that's what the stoic face comment is for. How did I just do? Okay,
no,
so yeah.
no reason for the stoic face. That's all correct. Like that's.
No, I know. I just mean like I don't really know what I did. So I mean like fumbled through it. So.
Well, I mean you fumbled through it,
but
but fumbling through it the first time is.
Yeah, that's kind of what I've been doing this whole year. So that's fine. Okay, so yeah, K1, and then this is them. That's all them. So we don't have to worry about that. And I guess next time we're gonna figure out the tail part. But
exactly.
You said, like, we've already pre-calced the end block, so it's not like we're gonna accidentally overflow or underflow here.
Exactly. So we've done every full block that we have, and now we're just gonna stick in the tail.
The last block, if there is one.
So 4, 5, 6,
the last half block.
7. So is there any questions about what we've done here to extract out 128 bits out of a string? Like,
I mean, not conceptually, like practice wise. I mean, this is like, yeah, I mean, calculating the length to get the number of 16 bit. Wait, length divided by 16 to get the number of 128 bit blocks.
Mm-hmm.
And then we don't use these or the seed. These are irrelevant for us right now. And then for every one of the 128 bit blocks, take 4 characters for each K,
Mm-hmm.
and use the bit shifting to copy them down into that 64-bit value, and then do some murmuring down here to mix and rotate. So yeah,
Yep.
no, I'm good so far.
Excellent. So yeah, and that's just about like practicing this kind of maneuver. So you see this a lot in like sort of the image handling stuff, for example, that was done in River City. I think there's a fair bit of code that looked like this, the mask handling and so on.
Yeah, right. Definitely mask handling, and yeah, like palette munging and all sorts of things.
So this kind of concept comes up a lot when you're doing that kind of data processing. So it's quite important. So let's call it there for today. Thanks for watching, everyone, and we'll see you next time.